So this final question involved a little bit of problem solving with powers of 2, powers of 3 and powers of 4 sequences. There's lots of different ways to approach these. I'm just going to tell you one possible way. So in 13a, I noticed the fact that 9 is actually the same as 3 squared. So therefore the question says 3 to the power of 5 times 3 squared. And because that then has the same base, I used index laws to realise that it was the same as 3 to the power of 7. So then I just look through the powers of 3 table, so power of 1, 2, 3, 4, 5, 6, 7, and so 3 to the power of 7 was 2,187. Right, in the next one down, I was doing 4 to the power of 5, so I'm looking through my 4s table, so 1, 2, 3, 4, 5. So 1,024 is 4 to the power of 5, divided by 2 squared, which I know is 4. So I did some of my bust up short division, 4s into 1,024. 4s didn't go into 1, so I carried that. 4s into 10 went twice, remained a 2. 4s into 22 went 5 times, remaining 2, and 4s into 24 went 6 times. So therefore my answer was 256. In the final question, we had 4 to the power of 6 divided by 2 to the power of 12. And this one involved a little bit of thinking outside the box. So if I looked at my powers of 4 table, 4, 16, 64, 256, I then noticed that those same numbers appeared in the powers of 2 table. So 4, 16, 64 appeared 4, 16, 64. So it's just that there was an extra gap between the two. So I was thinking then that 4 to the power of 6, so the one just here, would be every other column in the powers of 2. So 4 corresponded to 2 to the power of 2, 16 was 2 to the power of 4, 64 was 2 to the power of 6. So therefore, if this was 4 to the power of 6, that would be the same as 2 to the power of 12. So actually, this question can be rewritten as 2 to the power of 12 divided by 2 to the power of 12, and that is just 1.